Stanford University.
So when Jacek asked me to come and speak here, he actually gave me two questions that he wanted me to address in my talk. And the first was, does it make sense for large research or science applications or projects to move to the cloud, where large means 100 terabytes, petabytes of potential storage, big compute? And it's a fair question because there's been a lot of hype in the popular literature that clouds are going to solve all problems in research and science. So it would make sense to start there and share a few slides with you on my thoughts on that. The second question, well, if not petascale, up in the high terabytes, what is a reasonable scale and where will clouds really have a potential to make a difference for research? So I'll spend a few slides here and then I'll also show you some concrete examples. And as background or context for these comments I'm making, for the past 2 years, Microsoft Research has been offering tens of millions of core hours to researchers around the world in which to do research on Azure, core hours and associated storage. And with the exception of a small program run out of our Seattle office with some hand-selected projects, these resources have been given to funding agencies who are funding research, so they too can both select the projects and also learn and get the feedback on what projects are actually a good fit for the cloud and which ones weren't. In the US, it was the National Science Foundation. We're 1 year into a 2-year program there. Australia was with NICTA and CIRO. In Japan, the Implosion Project. A program in China starting with the equivalent of the National Science Foundation in China, and a number of agencies over in Europe. And to date, there's been about 100 such projects, research projects, that have been run through this program. And it was the responsibility of my team to actually help support these projects and guide these researchers as they're figuring out how to move their work up to the cloud. And very early on in the program, we were approached by a lot of the groups at national labs, in particular those doing metagenomics, like the talks you heard about this morning, where they had big compute problems and they needed to try to find some way to carry out their research. So we actually did some end-to-end studies where we actually got real data, ran it up on the cloud, computed the cost. We compared that with the cost of the clusters they have. And one of the real ahas we had very early on in the program is for heavily compute-intensive projects where they could buy a cluster and utilize that cluster 80% or above. The cloud was far too expensive. And we heard that today in the Netflix talk. There is a premium associated with running on the cloud. But when you're running these dedicated workloads and you can add just a little bit more hardware, be it memory, a little bit better disks, a little bit better networking, you can start to get orders of magnitude improvement over what you can run on the cloud. But again, that assumes 80–90% utilization for a large dedicated program. And one of the other ahas we had about this was that researchers are really bad about quantifying costs. The companies that you heard talking about using the cloud, they can very easily quantify their costs. They have to pay the staff. But a lot of researchers we found were very difficult. The building is purchased by the institution, the electricity and cooling by the department. My grad students manage the clusters. So it's going to be a long time before research organizations are going to look at the cloud and say, hey, this is a clear value win. That being said, many of these institutions do use the cloud for surge computing. But again, it's not a clear value prop for out of the door for compute. We all know in this room about the falling costs of storage, that it's basically storage is essentially free for all practical purposes. But there's a shock factor when you look at storage and the cost of storage in the cloud. And this slide was lifted from a blog back in September 2009. Sure, the numbers have changed a little bit, but it's the ratios that matter. The Backblaze blog pointed out that storage for the disks alone for a petabyte, I'm sure you can't see the number. I've been staring at it myself through the back of the room. 81,000 for a petabyte of storage, just the disks. Their product, 117. If one were to go to Amazon, and Azure is the same pricing, $2.8 million for 3 years to store a petabyte up in the cloud. Now, these numbers really aren't that fair. This article didn't point out the fact that in the cloud on Azure or Amazon, you get triply replicated storage. In addition to triply replicated, those are available storage access. There's at least a couple of other copies sitting around, or at least the capacity of the disk. So now we're talking 5 times the hardware. Additional racks, independent power supplies for fault tolerance, load balancers to ensure that you get good access. If you start to add all that hardware up, it starts to be on par with what you find in the cloud. And indeed, cloud providers don't make a lot of money, if any, on storage. It tends to be a loss leader. But still, there's sticker shock, and all of a sudden, to a research project, the dusty rack sitting in the back of their machine room starts to look very attractive for where to put a petabyte. So again, for large storage collections, this is a real hit, and especially with the 20 petabytes you're hearing about this morning in the talks. In addition, for those groups that absolutely have to move out to the cloud because of their infrastructure can't be expanded, power, or whatever, you find that the weakest link for the network, is going to basically slow things down, be it throughput or latency. And again, be it Amazon or Azure, just test the time it takes to push a terabyte or 10 terabytes up to the cloud, and any slow link along the way. And even those groups that are on national research networks such as NLR or I2 find that there's sometimes a little bit of a hitch along the way, be it the data center that the cloud provider's offering, the router, the load balancer. It takes a while to move extremely large data collections. And if you decide to use large or aggressive compression, the bisection bandwidth and the oversubscribed networks, you'd have to basically send your compressed data to the compute nodes and decompress it or do whatever you're going to do to get it in the form you want to get it in. You're going to find that's a challenge to push it through the networks as well. So these things are barriers. These barriers are lowering. I mean, Amazon, Microsoft have all made announcements. These are important workloads for the cloud in the future, so these barriers will be lowering over the time. But it certainly is a difficult proposition today. But if you take a step back and say, let's get some perspective on this. There was a US competitiveness in technical computing and research computing where they pointed out that of the 70 million engineers and researchers, and they classified that quite broadly, if they look at the very top of the pyramid, and most of the people in this room qualify up here, the very top have 80% of the iron. It's a good 80-20 rule. The 1 million users, be it cloud providers, large national labs, have 80% of the iron for doing compute and storage. The other 20%, universities, large universities, make up the second tier. The majority of researchers live in that bottom portion of the pyramid. And in fact, the majority, when asked, do you have to limit your research to the resources you have available, or can you just do what you want? The majority says, no, I have to actually shape my research down to the resources I have. And in fact, we're limited. And this is becoming an issue. So if you dig deeper into that and say, okay, so what would really enable these people? And if you talk to a number of these researchers, the first thing you find, most people are confronted with small amounts of data. And they're asking, I've got some data, what can I get? What insights can I get out of it? These people don't have a cluster or easy access to it. And again, it's 50 gigabytes, 100 gigabytes. That's where research starts to get slow for this community. The analysis itself, it can be compute intensive. When they do want to analyze that data, it can require a lot of compute cycles. The intermediate data products can be orders of magnitude greater than the initial input, so they better have lots of temporary storage, but then the final result tends to be rather small. And this is a very common pattern. Research projects are becoming much more diverse in terms of the participants, much more collaborative. There's a big push towards community reference data collections like we're hearing about from NCBI earlier today. Some of these even start at 5 to 10 terabytes, can actually support an entire community of researchers. It doesn't have to be in the petabyte range. In addition to the data, they're starting to have shared community-built supported research services like BLAST that you heard about. And again, for the ability for a community to share the same set of services and have the easy ability to dispatch them against reference data makes a difference. And then finally, as Alex Slay, I attribute this to him, he pointed out that software, and I'll say software services, are becoming a new type of instrument for research communities. And the analysis really involves the data that they capture and collect locally. Yes, there may be a reference data set up in the cloud, and then the ability to actually do that, have access to compute to carry out their analysis. And then for the whole community, where do you actually curate that result? So let me give you some examples. You heard about the large-scale BLAST run we ran earlier last year. But the real demand for our BLAST running on the cloud has been from the long tail, the small research community. They can't run their jobs on the NCBI clusters or their local university clusters. So one example, a group from PacBio and the Harvard lab at UW approached and said, look, we have to get a result. We're time limited. We were able to run that on the cloud in less than 30 minutes. The total cost for that, $150. Talked to NCBI, and the data set that runs 90% of the BLAST jobs, a whopping 50 gigabytes. So this is not a large reference data collection up in the cloud. And we have, of course, we can scale this out to as many research users that want to take advantage of this. Another example, this started with a researcher in Berkeley who was doing evapotranspiration, wanted to pick up data off NASA FTP servers from 2 MODIS satellites to build an evapotranspiration model. Could not get access to the resources at Berkeley, nor did they want to copy the entire database, which is in the hundreds of terabytes, to their server, and the rest of the community doesn't either. So what the PhD student and group built was actually a 4-stage processing pipeline that pulled the data from the FTP servers, roughly a half a terabyte up into the cloud, ran the entire pipeline, computed a year's worth of evapotranspiration model for the US, got a PhD out of it, total cost $1,800. And what's interesting is the number of students who have now come back later and started to modify it and do their research on this new service. because now they have the capability to move large amounts of data, and they can tune. And in fact, the actual analysis data is rather small, only 10 gigabytes, and they're curating that so somebody else who runs a different evapotranspiration model can start to compare them. And our most recent and last project I'll talk about is saying, look at the spreadsheet. That's where a lot of data lives. We'll be talking about this a little bit more tomorrow. How can we give a community the ability to write analytics models, machine learning models that live in the cloud? And from an Excel or any spreadsheet, there's a REST interface to this. They can actually connect. It'll upload their data, do the analysis, and pull it back down. These are the kind of tools we think that are appropriate for the cloud, and especially as it's built today, and can make a difference in research. So again, how do we move from what's on the left, where most of us live up at the upper top end of the pyramid, the need is down at the bottom, we can move over to the right and give researchers these resources. So that's it. Thank you.
For more, please visit us at stanford.edu.